Okay, so let's have a look at question 4. We've got a beam, looking at the cross-section of it. Shearing force from above is 2 kilonewtons. We need to calculate the second moment of area, the maximum shear stress, indicate its location, calculate the shear stress at point A. For 20 millimeters long, calculate the shear force at the joint between the vertical and the horizontal beams. Right. So the first one is straightforward. Looking at the formula sheet here. So for part A, what I suggest you do is when you've got an isometrical problem like this, you don't want to be using the parallel axis theorem, you want to use the void method. So treat this as a box with 2 sections cut out. So your eye is going to be a big box. Take away 2 of these sections. Okay, so you can treat the second moment of area just like an area. So, same deal works there. So your second moment of area formula is I d to the power 3 over 12. Hopefully you should know that without the formula sheet. I'll work in millimeters because it's more convenient. Okay, so looking at my big box, here I've got, now the only reason I can do this is because it's symmetric. So I know my neutral axis is bang in the middle. I've got no parallel axis theorems to worry about, and that's bang in the middle as well. So the B is 60, the D is 40 plus 15 times 2, so that's 70. And then divide by 12. And then we take away 2 of the void sections, so minus 2. So their width is what? It's not saying, but I'm assuming that, oh yeah, there you go, 15. I couldn't say it, 15. So we've got 60, take away 15, divided by 2. So the width of one of these sections here is 22.5. And the height of them is 40. 12. So what's that? 60 times 70 to the power 3. I'm going to do the divide by 12 last. Minus 2 times 22.5 times 40 to the power 3. Divide by 12. So 1475000, that's it, millimeters to the power 4. So let's divide that by 1 times 10 to the 12, get it into meters. That's 1.475 times 10 to the minus 6 meters to the power 4. So that's part A. part B, calculate the maximum shear stress indicates location. Well, the maximum shear stress for something symmetrical is going to be in the middle. Our shear, if we plotted what the shear stress is going to look like, it's going to be 0 at the top because there's nothing for the top to cling on to, so it has to be 0, and then it will go up a little bit as it goes through the section. Then the web will mean that it suddenly jumps up. We're going to get another kind of bend here, then it go down, and then be symmetrical, so that the maximum shear stress is in the middle. Right, so I want to use one of these formulas. So be careful. So we're saying shear stress. So the one I want to use is a shear stress, VQIT. The V is this value here. The I is the value I've just worked out. The T is going to be the thickness where we're trying to shear things apart. So T is 15 times 10 to the minus 3. Let's work in meters. So V equals 2000. The only thing we need to find is Q. And what is Q? Well, Q is going to be so we're trying to cut it in the middle here. So we need to know where the centroid is for this section and the centroid is for this section. You've got to imagine that these two sections are trying to pull away from the bottom section. And Q, you're given the formula for it, is the summation of A times centroids. So the bottom section will be a breadth, I'll work in millimeters, 15 millimeters wide, a height of 20 millimeters. Its centroid is here, so that's going to be 7.5, isn't it? Okay, and then the next one is find the centroid there. So plus the width of that is 60, the height is 15, and where's its centroid? Well, from here to here is 20, and then plus 7.5. Okay, so that's 27.5. So Q is going to be 15 times 20 times 7.5 plus 60 times 15 times by 27.5. So that is 27,000 millimeters. Notice its units to the power 3. Area times length. Okay, so I want that in SI units, so let's divide this by 1 times 10 to the 9. 3 sets of millimeters I need to convert. So that equals 2.7 times 10 to the minus 5 meters to the power 3. So I've got my values to stick into the shear stress equation here. So I've got 2000. Got Q of 2.7 times 10 to the minus 5. I've got I of 1.475 times 10 to the minus 6. And I've got a thickness of 15 times 10 to the minus 3. What does that all equal? So 2000 times by 2.7 times that to the minus 5 divided by 1.475 times by minus 10 to the 1.475 times 10 to the minus 6 times by 15 to the minus 3. Right, shear stress, so it's in pascals, so that's going to be 2.4407 megapascals. Okay, calculate the shear at point A. Right, so point A, you can shear either top or bottom. Makes sense to shear the bottom. So we've got a section here. I'm going to play a similar sort of game. The only difficulty is working out where that centroid is. So from here to here is 25 millimeters. That's what we're cutting. From here to here is 15 millimeters. So the middle of those two sections from this base here, which isn't the one I want, so I'll call this distance from base. Distance from base is 15 plus 25 divided by 2. So that's 20. So the centroid is about here, from here, and it's 20. What I want to find is this distance from here to the centroid. So that's going to be 20 plus 15, so that's 35. I think you're following this argument. So the distance from here to here is 35. The distance from here to here is 20. So the distance from the neutral axis to the centroid is 15. So what am I going to write that as? That's y is 15 millimeters. So I do a similar sort of Q calculation. So the boxy shape has got a width of 15 millimeters. It's got a height of what? 25. Take away 15. It's got a height of 10. And the y I found to be 15. So that gives me 200 and actually I should add on the other one first, shouldn't I? So the other one stays the same. Right, plus 60 times 15 times 27.5. So that equals 27000 millimeters to the power 3. Other than that, everything's the same as before. So the shear stress is going to be still 2000. The Q now is A. What have I done wrong? Did I do this wrong? Plus $60 times 15 times 27.5. Okay, gone wrong somewhere. Shouldn't be getting the same answer. So I've done something wrong. The width is correct. The area is less. The centroid shouldn't be the same, it should be a bit less. D is 20, 35, the centroid there is going to be, that's right. The Y looks correct. Okay. I'm getting the same answer. Maybe my previous answer was wrong. So 15 times 20. Yeah, the previous answer was wrong. The centroid will be 10, not 7.5. Ho hum. So that's 10. $15 times 20 times 10 plus 60 times 15 times 27.5. Okay, so that should be 750 . 75 times 10 to the minus 5 meters to the power 3. Yeah, I was looking at this 15 and I should have been cutting the 20 in half. Right, 5 times 10 to the minus 5 there. So let's do that again. Times by 2000. Divided by 1.475 times minus 6 divided by 15 to the minus 3. Okay, so put the inch, so 2.5085. So a little bit more than the location A. That's how I knew I was doing something wrong there. So I was expecting that to be a little bit more. We're there, and then A needs to be a little bit less. Okay, so that is hopefully okay now. For section, for a 20 millimeter long section, calculate the shear force at, what do you mean by a 20 millimeter long section? Calculate the shear force at a joint between the vertical and the horizontal beams. I think so in there is we've got an I-beam and $20 millimeters is going like this. And we're looking at putting bolts in. And we're interested in what the force is for that, for keeping a particular bolt in. So we imagine that the bottom one section is all one piece, and we imagine that we're trying to shear off that top section there, okay, and crack through the bolt. So the formula that I want is should be cutting and pasting them really. So it's this one here. Now with this, be careful how many bolts you're cutting through. So in this particular scenario, I'm only going to cut through one bolt. So I'm going to imagine the top section trying to pull away from the bottom section. So I've only got one force here. So what I need to do is work out the Q for this top section. Okay, so Q, that's straightforward Q. AY. Well, said that, made a mistake last time. Get another picture of that cross section. Okay, so the middle from here to here is 20. So to get from here to here, it's, yeah, so it's, we're just doing this calculation here. So Q is 60 times 15 times 27.5. 60 times 15 times 27.5, that's all in millimeters. So power 3 divided by 1 times 10 to the 9 to make it into meters. Okay. Right, so that's Q done. The separation length we're saying is 20 millimeters. So H equals 2000. Yeah, V still 2000. Q is 2.475 times 10 to the minus 5. Separation was 20 millimeters. So 20 times 10 to the minus 3. And the I was what? Use that value there. So 1.475 times 10 to the minus 6. So that's the faults that we need to cut through the bolt. 2000, 2.475 times that. Whoops, what am I doing? Go away. 2000 times 2.475 times this to the minus 5 times 20 to the minus 3 divided by 1.475 times that to the minus 6. So that's a force 671.2 newtons. Yeah, that's it. That's all we have to do.